let me know when you can all see it. Cool. All right, so I think at last lesson, it was a while back, so I'll quickly recap you all. We went through pedigrees, Punnett squares in particular. When do we use Punnett squares, Rithanya? What kind of exam questions would prompt you to use a Punnett square? Because they won't tell you in the exam, use a Punnett square in every question.
To like determine like phenotypes and genotypes.
Yep, of offspring. That's the main thing, right? And what must you be given to do a Punnett square? Edward? What do you see in all these questions that's been shown here? What must be given for you to do a Punnett square?
Sex-linked or autosomal, recessive or dominant.
Exactly, the pattern of inheritance. So the two things you all need to write down or have jotted down is Punnett square is for offspring, genotypes, phenotypes when you know the pattern of inheritance. But the reality is sometimes you will not know the pattern of inheritance. You may come across, let's say you're working at hospital, or if I come across a patient and have this weird genetic disease, right? And it's in some family members, it's not in others. I have no idea what the pattern of inheritance is. The first thing I'm going to do is take a strong medical history where I find out every single person in that family who has the disease and doesn't. And the goal for me first would be to find the pattern of inheritance. Because once I've done that, I can then use a Punnett square and determine the likelihood of their child having the disease, etc. Right? So can you see the raise hand icon? Have you done pedigree questions over the holidays? Just so I know how fast to go with this content. Good. Ed has. Okay. Matthew, Alyssa. Okay. Some of us have done pedigree questions, some of us haven't. That's all right. Okay. So pedigree is actually very intuitive. When you look at this, you kind of see a family tree. Everyone appreciate that you can see people being connected. Circles and squares represent individuals, right? Now, a little bit about how to read pedigrees. We'll start off with the shapes. Alyssa, what does a square represent? What does a circle represent? And what does being shaded represent?
A square represents a male and a circle represents a female. And I think if it's shaded, then it means that they're affected.
Good, very good, right? They're affected by a condition. Sometimes it doesn't even have to be a disease. It could be red-green color blindness, which is more of a variation. It can even be brown hair, right? So it's just affected. We don't know whether this affected trait follows a recessive or dominant pattern. That's what we're trying to figure out. So remember, the goal of a pedigree is you're doing a huge family tree to find out what the pattern of inheritance is. Is it dominant? Is it recessive? Is it autosomal? Is it sex-linked? Okay, good. So now we understand the shapes and the shading. The next thing is the lines connecting the individuals. So Matthew, what does this horizontal line between individuals represent?
It's pretty much just offspring. Yeah, not really, but just the link between them.
Yes, the horizontal line. So this line represents a marriage line. That's what it represents. Okay, so horizontal line between two individuals is a marriage line. Okay, those are the parents. Good. And as Matthew alluded to, this line from the horizontal line, Ed, what does this represent? The blue.
The relation to parents.
Yeah, good. So offspring line, right? So a horizontal line between two individuals always represents a marriage line. Okay, and a line down from that horizontal line represents all the possible offspring. So in yellow, I highlight again, these are all the offspring from the marriage line, which I'll highlight in purple. Okay, that's quite literally it. That's all you need to understand about pedigrees. A few other things you'll note is, does anyone know what this line represents? I have actually never seen this in my 7 years in exam questions. They don't ask you many questions with this line. Does anyone know what this inverted V represents? Kruti, what do you think? Oh, yeah.
Twins, maybe?
Yeah, very good, right? It represents twins. So usually twins that have the same genotype and phenotype. So you might get a question on that in the HSC. They do love asking completely new question types, right? Very good. Next thing is, what do these numbers represent? So why do we have a 1, 2, a 3, and then individuals being numbered? Tul, what does a 1, 2, and 3 represent that I've circled?
It's like the generation.
Very good. So when I'm referring to a person, and this is very important for your exam questions, if I'm trying to talk about this individual and their genotype and phenotype, I'm not going to say the person in the far right bottom with a square who's unaffected. That's not how you communicate pedigrees. I will be mentioning individual I4, meaning this individual is in generation 3 and he's the 4th individual. We always number them from left to right. Now, this is probably the most important thing I'll tell you about constructing and interpreting pedigrees. If you are going to create your own pedigree, the one thing that most students miss out on in an exam, can anyone tell me? If you were to draw your own pedigree, what do you think is the biggest thing that most of your peers will miss out on in their exams? Any ideas? Let's go to Sarah. Anything you'll try not to forget in an exam, Sarah, about these pedigrees?
The numbering of the generations.
Good, close. Starts with K, has 2 letters. Those who've done pedigree questions should know.
The key.
Very good, right? You don't realize how many times you'll forget this and then lose, easy 2 marks, right? If you are ever to draw a pedigree, and I know it's assumed knowledge, you'll all know this. After you do hundreds of pedigrees, obviously know a square is a male, a circle is a female. But if you do not represent square equals male, circle equals female, and then represent, you can use a diamond. Diamond means indeterminate gender. We don't know the gender, but you can shade it to show this is affected, right? If you don't have these 3, unfortunately, we'll lose a mark. Okay, so in terms of exam technique, never forget a key if you're drawing a pedigree. Does anyone have any questions? Pedigrees aren't too bad to interpret, but we're going to start jumping into how to quickly answer pedigree questions. Good. All right, so you guys can do the practice pedigree construction questions in your own time. So I'm going to asterisk this page. I want you to do these questions. And if you already have, very good, right? And ideally, where I would have wanted you all to be at now is finished reading the Mod 5 notes, doing the questions, and then doing all the Mod 5 trial questions, right? And if you've started Mod 6, that is a plus because it's going to help in terms of being ahead of school. Good. Now, this part, analyzing pedigrees, is probably more high yield than drawing pedigrees. Most likely in your exam, one of your MCQs in your final HC exam will be a pedigree question, which you'll need to interpret. Does anyone know or have a strategy? Can you just hit the raise hand? I won't ask you what the strategy is, but do you have a strategy to how to interpret a pedigree? That's all right. So this is the thing. With questions like pedigrees, analysis, even those questions where you're calculating allele frequencies, if you don't have a set of steps or a template, you'll stuff up in a really tough question because you won't have a set of steps to follow and some solidarity in that sense. So let me give you an example of a pedigree like this, right? If you're stressed out in the exam, you've got 2 minutes left, probably fumble the question. But if you have a set of steps to follow, you can almost robotically go through this question and always get the answer right. Now, I'm not going to go through this question first because it's not asking the most common question, which is what is a pattern of inheritance? I'll go through this one because that's exactly what it's asking us. What is the pattern of inheritance for this pedigree? Now, I want you to just look at the pedigree and tell me, just common sense wise, what does it look like to you? This is a family tree. There's some shaded individuals, some unshaded individuals. If this was to be a dominant or recessive trait, how would it differ in appearance? Just eyeballing it. Rithania, how would the pedigree look different if it was dominant versus recessive?
I guess if it was dominant, more people would have the trait.
Yeah, very good, right? So typically, if it's dominant, it usually doesn't skip generations, right? And you can see that here. This trait is not skipping generations. Every single generation has some affected people, right? So it could be dominant. We're just guessing right now, right? Playing pure guesses. Alyssa, what if it was sex-linked or non-sex-linked? What would you see in terms of the gender?
If it was sex linked, I think like one of the genders, I think everyone would have it.
If it was sex-linked, everyone would have it. Let's take a pause and think about
every for example, I think if it was like a disease that affected males, then pretty much almost all of the males would have it.
Very good. And let's just to follow up on that, would that be in a sex-linked recessive or sex-linked dominant condition?
Not too sure.
That's all right. Let's go to Atul. Atul, what would you expect in a sex-linked recessive condition? Any ideas? So Atul, sex-linked recessive, yep.
Not really sure. I reckon just the expression rate would be lower.
Okay, right. Now, generally, when you're providing some kind of explanation, I want you to always ask yourself why, right? So if you mention expression rate is lower, why would the expression rate be lower? And then that would eventually lead you to, what does it even mean to be sex-linked and sex-linked recessive? Like I told you, 99% of the time in real life, it's sex-linked recessive. Sex-linked dominance is a very, very rare pattern of inheritance, right? But remember, in your HSC exams, it can throw you anything. But in reality, for example, I've never ever seen a sex-linked dominant genetic condition. I've seen many patients with sex-linked recessive conditions. So what does it mean to be sex-linked, and specifically sex-linked recessive? To be sex-linked, you lie on the X chromosome. Everyone agree? How many X chromosomes does a male have versus a female, Matthew?
I don't remember.
So, right, so female is XX, right, 2X. So I want all of you to pay attention. This is very, very high yield, right? I'd say even more high yield than pedigrees because it's kind of like the foundational information for you to even answer pedigree questions, right? Remember, sex-linked literally means lies on the X chromosome. Females have 2 X's, males have 1 X, right? And they have 1 Y. It's the Y chromosome that has genes that enables differentiation and development of the male reproductive system. Okay, good. Now, remember what I said, the Y chromosome is like a degenerate X chromosome. It's so tiny. In reality, it's like X is like this big, and the Y chromosome is like just broken, deteriorated, right? It doesn't have many genes. So I want you to assume the Y chromosome doesn't carry any alleles, right? So if a condition is sex-linked, we said it means it lies on the X chromosome. Males only have 1 X chromosome, females have 2. So females can carry 2 alleles for a sex-linked condition. Males can only carry 1. That is the first difference that makes this pattern of inheritance completely different to autosomal. Because autosomal, everyone has 2 copies, right? Because everyone has 2 homologous chromosomes, 2 alleles for a gene. In this case, males only have 1 allele, right? So I want you to now imagine that this male and this female are both unlucky and they inherit a recessive allele. Ed, what does that mean for the male? Is the male immediately affected, or does he have any chance to stop himself being diseased by this sex-linked recessive condition?
He can got a stronger chance of not getting it.
Oh, as in he's affected. Do you agree? So if we're talking about a sex-linked recessive condition, little r is disease. Remember to write that down. So this male, he's got the little r, and he has no other spot or slot to inherit another healthy allele that can mask it. So the male is affected. The female can still inherit another allele. And if she inherits a dominant allele, she's good, she's healthy. She's a carrier, meaning she can still pass on this unhealthy little r, but she's unaffected. And so the implication for this is since males cannot mask, aka they don't have another slot where they can inherit a healthy allele, they cannot mask X-linked recessive conditions, whereas females can. Since they have a second allele, they can inherit a healthy dominant allele and mask X-linked recessive conditions. So what that means is since males cannot mask the conditions, they're more likely to be affected. So the rule of thumb you need to remember is if you see a pedigree where every single male or most males are being affected, your brain should be thinking sex-linked recessive. Is everyone with me? Put your hand up if you have any questions at all, right? I'm more than happy to answer, but I want to make sure all of us are on the same page. Good, right? So key point here. Well, do we see that up here? Sarah, do you see most males being affected?
Yeah.
Looking up at this pedigree, how many males are affected? How many females are affected, Sarah?
There's 4 males that are affected.
Close. So the circles, remember, are females. The squares are males.
Oh, sorry. So 1 male is affected.
Good, right? Only one. There's so many males here, only one's affected. So I would try to be thinking this is not a sex-linked recessive condition, right? What about with a sex-linked dominant condition? What would we expect? This is an open question. I don't want to ask just any one person. What would you expect to see in a sex-linked dominant condition? Would there be a predilection for females being affected? Or would there be an increased likelihood of males being affected? Do you think? Let me help you out. What does it mean to be sex-linked again? So let's go to Rithanya. Rithanya, what does the word sex-linked mean?
Lies on the X chromosome.
Good. So straight away, male, female. Male is XY, female is XX. So as Rithanya said, sex-linked means lies in the X. So females have 2 X chromosomes, they have 2 alleles. Males have 1 X chromosome, 1 allele, right? Now, if we use the word sex-linked, or you can use X-linked, dominant, Rithanya, what does that mean? Is capital R equal disease, or does the little r allele equal disease? When I say sex-linked dominant, Rithanya?
Is it capital?
Yeah, very good. So capital R equals disease. Okay, good. So when we look at a male, there are 2 possibilities for what allele this male can inherit, right? Matthew, what are those 2 possibilities?
Inherit a capital R and little r.
Good. There's a
Yeah.
1 or 2, right? You can inherit a capital R, which is a dominant allele, or this male can inherit a little r. Those are the 2 possibilities. That's a sample space. So it can be a capital R or a little r, right? If he inherits a capital R, Matthew, is he affected?
Yes.
Good. And if he inherits a little r, Matthew, is he affected?
No.
No, good. This is exactly the logic all of you should be following when I asked you that question, right? If any of you are answering those big, hard questions with a yes or no, then your line of thinking is flawed, right? I care way more about how you rationalize and explain those questions in your head. This is the most important stuff in biology, right? Now, let's have a look at the female. The female has 2 slots. Okay, so in the first slot, just as Matthew said, you can inherit a capital R, which makes the female automatically diseased, or a little r, where she's safe. But is she really safe if she inherits 1 little r? No, because a female can inherit 2 alleles. Everyone with me? So even though this female has inherited 1 healthy recessive allele, she needs to play this bad luck lottery game again. And she still has a chance to inherit a capital R. And what phenotype would this be, Alyssa? Would this woman be affected if she inherited a second capital R?
Yes.
Exactly. Right? So unlike the male who's safe the second he gets 1 little r, the female, when she gets 1 recessive allele, she'll still need to inherit another allele and has a chance of getting this dominant allele. And so what this means is with sex-linked dominant conditions, someone tell me, who's more likely to be affected, the male or the female? The sex-linked. Very good. The female, right? The female is more likely to be affected because she has to play this bad luck lottery game twice. Right? Imagine having to flip a coin heads or tails, and if it's heads, you die. Females have to flip the coin twice, right? Males only have to flip the coin once. I would rather flip the coin once rather than have to flip it twice, right? And so that just crude analogy explains to you that females are more likely to be affected with a sex-linked dominant condition. So what this means to you all, right? Rule of thumb, sex-linked recessive, you're looking for males being affected. Sex-linked dominant, which is very rare, you're looking for more females to be affected, right? And if you look at this pedigree, you can kind of see it could be sex-linked dominant. The ratio, as Sarah mentioned, was there are 4 females being affected, 1, 2, 3, 4, to 1 male. It could be sex-linked dominant, right? So far, everyone, we've just eyeballed this pedigree and we've made some guesses, right? I'm going to show you the 2 or 3 questions you can ask yourself to answer pedigrees in under about, I do it in under about 10 seconds. So I'll give you an example. If I look at this pedigree right now, I can tell you that it could be autosomal recessive. And that took about 3 seconds. Let me explain what my brain was thinking in that time to answer this pedigree question, right? So I'm going to rub all this out. Okay. The first question you ask yourself is a question that you and I have been going through just then, which is males versus females. Are more males affected? Are all more females affected? Right? And if more males are affected, then you remind us, what's a pattern of inheritance possibly?
Sex-linked recessive.
Good, sex-linked recessive. And Rithania, if more females are affected, what would be the pattern of inheritance?
Sex-linked dominant.
Yeah, sex-linked dominant, right? These are just guesses, right? We can't be sure, and I'll show you how to be sure at the very end, okay? Good. So looking and applying that to this pedigree, well, I go, well, it does look like more females are affected. So this pedigree could be sex-linked dominant. It could be, we don't know. The second question I ask myself, pay attention to this. I'm looking for 2 parents that are 1 color and a child that is the opposite color. Where do we see that? Look at this pedigree. You could ask a kindergarten kid, right? Tell me 2 shapes on the same level that are the same color and a shape underneath that's the opposite color. Where do you see that? Can someone raise their hand and try to explain it to me in terms of generation and individual number? So what would you identify the parents as and what would you identify the child as? Let's go to Atul. So which individuals or which parents are 1 color and the exact opposite color to their child?
Generation 2, 1, and generation 2, 2, and then generation 3, 1. I mean, generation 3, 2.
So you said generation 2, 1.
Yeah,
So that's generation 2. That's individual 1.
yeah,
And then generation 2, 2. Is that what you said?
yeah.
Yeah. So generation 2, 2. Okay. So those are the children, right? So usually when you're explaining like the parent-child, you explain the parents first. So I'd say generation 1, individual 1. That'd be here. Generation 1, individual number 1. Generation 1, individual number 2. So those are two parents that are the same color. They're white, right? And then you can see that the two children that Atul's mentioned, you just need to pick one. You don't need to pick both of them. So I'll just pick this person, generation 2, individual 2, right? Which is the exact opposite color. Now, can anyone tell me what is this telling you? When you see two parents that are one color, a child that's the opposite color. In terms of autosomal inheritance, there is only one possibility in which this could happen. I want you guys to think. I don't want to spoon feed us. When would you see in autosomal inheritance that two healthy parents would produce a diseased child, or a child with a completely different characteristic to either parent?
Doesn't it have to be recessive? So
Good.
when it's recessive, yeah.
So what would the genotypes of the parents be? What would the genotype of the child be?
Capital R, lowercase r, capital R, lowercase r.
Good. And for the child?
Lowercase r, lowercase r.
Very good. Perfect. Right? So good job, Atul. So the conclusion is whenever you have two parents that are one color and a child that is the opposite color, the only way that can happen in terms of autosomal inheritance is when you have heterozygous parents that each pass on a recessive allele that they've masked to a child. And since the child did not have a dominant allele, right, they're going to be a completely different genotype to either parent, and in this case, a completely different phenotype. So rule of thumb here is whenever you see two parents of one color, child of the opposite color, the parents must be heterozygous, child must be homozygous recessive. And this is assuming it's not sex-linked. Okay, this is assuming autosomal inheritance, so no X's, no Y's. Okay, so the second question you ask yourself is, do you see this pattern? Where two parents are white and the child is a different color, or do you see the exact opposite? Right? I'm putting a diamond just because the gender doesn't matter. You're just looking for a child that's affected or unaffected. What would it mean in the second case? So look at what I've drawn here. Right? Let's go to Kriti. Kriti, what inference can you make in terms of autosomal inheritance about this little pedigree that I've drawn? Right? What would the genotypes of the parents and the child be?
Lowercase r, lowercase r.
Yeah, for the child and the parents, just like the previous question.
Capital R, lowercase r.
Yeah, heterozygous, very good, right? But the difference here, if you can all realize, is it's telling you a completely different pattern of inheritance. In the pedigree at the top, this one right here, what you're determining is now little r equals disease, because the child is shaded and they must have a homozygous recessive genotype. So that means this condition is autosomal recessive, right? Since little r equals disease, right? But if you look at this inverted color, right, where the parents are affected, the child is unaffected, little r equals to, remember, it's not shaded, so little r equals to no disease. So that must mean that big R equals to disease, or this condition is autosomal dominant. That is how I answered this pedigree question. Right? Good. So these two questions, I want you to realize, they give you a very highly likely educated guess as to what this pedigree could be. Right? So right now, all I've determined is this condition could be, number one, sex-linked dominant, which I told you again was unlikely, right? It's just a very rare pattern of inheritance. Or more than likely, it's probably autosomal recessive, because we saw this pattern here, right? So little r equals disease could be autosomal recessive. So in an exam, what you typically would do is you go, okay, it's probably autosomal recessive. Let me either fully complete this question, or I can come back to it when I have time and fully answer it. Okay, so far I've given you 2 questions that allow you to make a highly educated guess as to what this pedigree is. Does anyone know how to conclusively, with 100% certainty or close to it, determine what the pedigree is? Because right now we've got 2 options. And I've just said pick B, autosomal recessive, because sex-linked dominant is not as common. So you're just guessing at this point. How do you tell with certainty which one it is? Because that's what this question is asking. Does anyone know the final thing we must do to answer this pedigree?
Fill out the pedigree and see if it works.
Exactly, right? So the final step here, step 3, it's probably the most cumbersome step, right? But you can get really fast the more questions you do, is the only way to confirm or disprove a pattern of inheritance is to assume it and work through the entire pedigree and see if there are any errors. If there are no errors, that pattern of inheritance is possible, right? So what I mean by that is the only way to determine if this condition is sex-linked dominant or not is to assume it is sex-linked dominant, find out every single person's genotype, and look for any errors. And if you see an error, you cross this out. If you don't see an error, it could be that pattern of inheritance. And then you have to do the next. The same thing for autosomal recessive, right? You assume that pattern of inheritance, right? You look for any errors in the pedigree. If there is an error, cross it out. Now, this sounds very long. I'm going to show you some tips and it'll be very easy. You'll be answering these questions in under a minute, right? So rubbing all of this out, in your 3-second analysis, you have confirmed this could be X-linked dominant or autosomal recessive. Okay, let's start with autosomal recessive. So what we're doing now is we're assuming, this is the final step, we're assuming the condition is autosomal recessive. So if we're assuming it's autosomal recessive, remember, little r equals disease. Okay, so what can we do now, Sarah? What can we write as the genotype for every single affected person? If you're affected, what must your genotype be, Sarah?
Lowercase r's 2.
Good. So blindly find every single person you can and write 2 lowercase little r's. That's exactly what you're going to be doing, right? And every person that's unaffected, I'm using diamond because we don't care about gender here. What would their genotype be? Let's go to Alyssa.
It could be capital R or capital R lowercase r.
Very good. So it could be capital R and then any possibility for the second allele. So what we're going to write now is for every single unshaded person, we're going to write capital R dash, because we don't know what the second letter could be. As Alyssa said, it could be a little r, could be a capital R, doesn't matter. So what we're going to do now is write capital R dash next to every single unaffected person. Now, don't be like me. Small thing is always write the genotypes on top of the box, only because when you write at the bottom of the box, you might confuse it with this person in an exam, right? So just have these little tips, but they'll make you avoid silly mistakes. Okay, I'm just going to do it this way, but for all of you, just write it at the top. Okay, so capital R dash, capital R dash. Okay, good. Now we fill out the rest of the pedigree. So we can start using logic here, right? These 2 parents, and I think we've already figured this out, right, had a child with 2 little r's. One allele came from each parent, so 1 little r must have come from this parent, 1 little r must have come from this parent. Is everyone with me? Right, so now we're starting to fill out this pedigree. Okay, what about this person, this box? Could that be, does it have to be a big R? Does it have to be a little r? Could it be both? What are we thinking, everyone? At all? Generation 2, individual 3. What is in the box? A little r, a big R, or could it be either?
Not sure.
So think about this, right? They've got 1 capital R. Could have come from any parent. We can assume, okay, that it, let's just say, came from this parent. Okay? The second parent has a capital R and a little r. Either of those 2 letters can go into the second box. The answer is it could have been either. We don't know at the moment. Is everyone with me? This is how you determine every single person's genotype. Okay, so what I'm trying to say here is for this person, we do not know. Don't have enough info. And that's completely fine, right? We're just trying to disprove. We're trying to find errors, right? If we don't know what that is, it doesn't matter. How about this person here that I put a dotted line around? Generation 2, individual 4. What must their genotype be? What's in this box? I'll go to Matthew.
It has to be little r because its offspring is infected.
Good, right? So you can see an offspring that's affected. So obviously 1 little r came from 1 parent, the other allele came from another parent. Very good. Good job, right? So now this box must be a little r. Good. What about this box here? Britannia, what must this individual, generation 3, individual 2, what must that letter be in the box?
It could be either, right?
Are you sure? Think really hard. There's a big R here. Who must the big R have come from? This person or this person? 1 or 2? Where did the big R come from? Look at the letters in top of individual 1. Look at the letters next to individual 2. Who has a big R?
1 does.
Very good. So the big R must have come from 1. 2 can't provide a big R. It's not possible. So that means the other allele came from individual 2. So Nathaniel, what must the letter be in the box?
Small r.
Very good. Small r. Good. And finally, we have this person and this person, right? What must this person's letter be? I'm going to go now to Alyssa. So generation 1, individual 3. What letter do they have?
It would be a lowercase r.
Very good. See, now you're all thinking, right? Using the letters here. There's 2 little r's. 1 little r came from this parent. The other must have come from this. Easy. Very good. Good job, right? And now going to generation 2, individual 1, 2, 3, 4, 5, 6. Individual 6 in generation 2, this person here. What must this letter be? Let's go to Sarah.
A small r.
Very good, right? The big R must have come from here. So little r came from the other parent, right? Little r. So now we finished this pedigree. And remember, we took a long time because this is your first time doing it, and I'm taking you through the thought process. But when you get to exam level ready, you'll be doing these in like 20 seconds. Okay, so now tell me, do we see any errors in the pedigree? Look at the parents, look at the child. Were there any times where it was impossible for a child to have a particular genotype from the parents? Yes? No? This is possible. This is possible because the 2 little r's, we already explained that. This is possible. This is possible. This is possible. because it made sense. Remember, we determined every child's genotype, so the pedigree makes sense, right? So when we went through this entire pedigree, we determined everyone's genotypes, we were able to logically work it out. And it correlated to whether they're affected or not. AKA, this person had 2 little r's, they must have been affected. Or this person had a capital R little r, and they were shaded white, unaffected, right? So what this is telling you is that this condition definitely can be autosomal recessive. And at this point in an exam, where you've assumed autosomal recessive, it completely works, you can confidently put your answer down as most likely being not sex-linked and recessive, aka option D. Right? They will never give you a question asking you what is the most likely type of inheritance if both X-linked dominant and autosomal recessive completely work in the pedigree. Right? But since we've come to one answer working, that must be the answer. Okay? If both of them worked, they would have asked you what 2 types of patterns of inheritance are possible for this pedigree. And that definitely can be a trial biology question. Okay, now we're going to use the same question and we're going to apply X-linked dominance. And now I'm not going to say anything. I'm going to give you all about 40 seconds to a minute to try this pedigree out. Assume it is X-linked dominant. It's a little bit harder, but I back you guys. Assume it's X-linked dominant and tell me, does it work? Are there any errors in the pedigree? Okay, give it a go. And if you find an error, hit the raise hand icon. Good. I'm gonna get some water. Be right back. Feel free to take a little break, get some water as well, and please stand. This whole week, my first week of hospital was all just orientation lectures. That was so boring that I was nodding off, and it was because I was sitting down nonstop for hours and hours. So make sure, you know, every 40 minutes or so, you're standing up, stretching, getting some water. Okay, So maybe I'll give you guys a minute or so to stretch, stand up as well. But has anyone come close to answering the question? Does X-linked dominant work? Give you guys a bit more time. Good. Who's still working on it? Can you hit the raise hand icon if you're close to an answer? Good. All right. Give you a bit more time. Anyone unsure how to approach it? That's also completely fine. This is a decently important skill. I remember in my 5th year uni exams, we actually had a genetic station, which was up to 25% of our exam. So our exams were verbal, we have to actually talk, which is pretty cool. Makes the exam much more fun than writing. But they would give us a pedigree and we'd have to answer it and then answer further genetics questions. So this is quite an integral skill to being a doctor in 2023 onwards. As you guys know, everything is shifting to more genetics, DNA sequencing to diagnose conditions, and we're finding the genetic basis for so many different non-infectious diseases, right? The cause of heart disease, why certain ethnicities have a higher likelihood, etc. Okay, so maybe I'll start us off. Anyone got an answer yet? Good. Alyssa, what was your answer? Does it work or does it not work?
I don't think it works.
Good. All right. Yeah, I'm not going to ask you exactly how because we'll come to that now, but good. Very good, right? So let's assume it's X-linked dominant, right? And remember, whenever we're assuming, I like to write a few things so I don't make silly mistakes. So what I usually write is assume X-linked dominant, right? And once I've done that, I go, okay, well, is capital R disease or is little r disease? It's a very basic thing to write, but it helps so much. So capital R equals disease, right? And then what I do is I go through every single shape and shade and I determine what their genotype must be, and then I fill it out. So I go, okay, well, if I'm a male, I must be XY. If I'm a female, I must be XX, right? And if I'm a male who's not diseased, what letter must I have in this little dash? So this male right here. So let's go to Matthew. Matthew, what letter must this male have?
Little r.
Good, right? So I fill that in, and then I go to every single male who's unaffected. I follow these exact same set of steps, even in the exam. But the second you start, mixing it up, that's when you start making silly mistakes because you're stressed in an exam. You're actually not performing at your most optimal, right? You're most optimal when you're at home, you're calm, you're thinking straight. So, all right, so I go, this is XY, and I know it must be X little ry. So every single unaffected male, I'm going to just blindly write X little ry. This time, I'm going to do it correctly and write it on top. X little ry, and that's all the males. Good, so then I move on to the next shape. Well, this is a female without the characteristic. So what letters will I write for her? Let's go to Edward. Edward, what letters would you write for a female without the characteristic?
Either capital R, lowercase r, or capital.
If it was capital, Ed,
Sorry,
which you,
the recessive would be homozygous recessive.
very good. Good job. Right? So that's why this helps so much. Because if there's even one capital R, she should be diseased, right? Good. So now, next to every single unaffected female, I'm going to put X little r, like this. X little r, X little r, X little r, X little r. So I'm not even thinking right now. I'm just copying down what I wrote. Now, to be a male with the characteristic, what must my genotype be? Let's go to Critty. What must my genotype be if I'm a male with the characteristic?
Capital R.
Good. So now next to every single shaded male, I'm going to put X capital R Y. And there's just one shaded male. Good. I can actually probably stop right here because I straight away see there's an error. Can everyone tell me what the error is? And here's another tip. You know this region here where we found our initial parents of one color and the child of the opposite color? That is the high yield part of the pedigree. That is usually where you'll disprove everything else, and that is where you'll prove your pattern of inheritance. Remember this, that two parents of one color, child of the opposite color, that is the area where you'll be able to disprove pretty much all the other patterns of inheritance. So just looking there, is it possible for parents who only have little or lowercase letters to have a child with a capital letter? Remember, we're not talking about mutation. There, you don't assume mutation has happened from parent to offspring. Is that possible? Not at all, right? You can't just make a capital R out of thin air. So we have disproved sex-linked dominant. Remember, you wouldn't have even done this in this exam question. We only did this so you test it out, and so you kind of get comfortable working and actually assuming and disproving patterns of inheritance. But can everyone see the steps to answer a pedigree? 3 steps, right? First step is, are more males affected or are more females affected? And then you can guess whether it's sex-linked dominant or recessive. Second question is, are there 2 parents of one color and a child of the opposite color? And that will tell you straight away, if it was autosomal, it'll tell you the exact pattern of inheritance. And the final step is, right, within a minute, try doing this as fast as you can, assume the 1 or 2 patterns of inheritance you have, assume one of them, and see if they work. If that pattern of inheritance works, then that's the answer. If it doesn't work, then the other pattern of inheritance you have as an option must be the only answer. 3 steps, you can answer every single pedigree question. Doesn't matter if it's a HSC question, it doesn't matter if you're a surgeon answering a genetics question. Those are the 3 steps you'll always be using. Any questions at all? Please ask away. Yep, Critty, question?
You know, in the step 2, how there was like 2 not affected and then the offspring was affected. Is that where like the carrier comes into the pedigree, or is that different?
So when you use the word carrier, you're specifically talking about sex-linked recessive conditions, right? So that's a unique case. Remember, when we're looking for 2 parents of one color, child of the opposite color, we're assuming that it's an autosomal pattern of inheritance. Okay, so assuming it's not about X's and Y's, it's all about capital R's and little r's. So this part here, right? And we go, the parents are heterozygous, child is homozygous recessive. We don't call these people carriers per se in HSC. In the real world, we use it all interchangeably. If you have a diseased allele but you don't express it, you're carrying it. But in the HSC, when they use the word carrier, really they're most commonly talking about this scenario where a female has one recessive diseased allele that she's not expressing, but she can pass on to offspring. That's when you use the word carrier. So I wouldn't use the word carrier when I'm talking about this pattern here. This pattern is just telling you parents are heterozygous, child is homozygous recessive. Okay, we do not call this carrier in the HSC. Does that make sense?
Yeah.
Yeah. But in the real world, every case where there's a recessive allele that's not being passed on, like this one, that could be passed on, And even in this case, they're both called carriers. Okay, it's just the word carrier is a very specific term for HSC, so be careful how you use it. Good. Any other questions at all? Good. All right. I'll give you one more pedigree question, then I'll give you a proper 5-minute break, right? Let's go to right. Give this question a go. 2017 HSC. Usually a pedigree question will be an MCQ question. Will only be 1 mark. Pay attention. It's usually the questions 14 to 20, right? Meaning you're fine to spend a little bit longer than a minute on it. Questions 1 to 10, you should be spending a minute or sometimes even less than a minute answering it. And just remember, question 16 to 20 of your MCQ, I can guarantee all of you will have at least 1 question that is going to be very challenging and take even up to 5 minutes. So don't be worried or anxious if you're spending a lot of time on one of those MCQs. Every year it's like that. Good. So I'll give you all about a minute and a half to do this question. If you have any questions at all, feel free to ask it now. Even general biology study questions, more than happy to answer. Who's sitting the UCAT for medicine or dentistry this year? Good. So all of you by now should have got the Medify. I prefer Medify, but some people use MedEntry as well. The question bank, and you should be treating it like a whole 2 units of another subject. Okay? And make sure you time yourself always. That is the biggest thing. The exam is not hard. It's just very fast. You need to answer some of those questions in very quick succession time. Okay? All right. Let's get started. Brittany, what's the first question you ask yourself looking at this pedigree?
Which gender is more affected?
Good. Do you see tendency for males or females to be affected?
There are more males affected.
Good. There's 3 males and 2 females, but is there a strong male or female disposition in this pedigree? It's 3 to 2. I wouldn't say that's big. Usually in a sex-linked condition, you'll see like 6 to 1, or you'll see like 7 to 1, or literally every single male is shaded, right? So 3 to 2, I'm not too worried. I'm thinking, okay, it's probably not sex-linked. Okay, that's my educated guess. Number 2, what's the second question you ask yourself? Let's go to Edward. What's the second pedigree question you ask yourself, Ed?
I can't remember.
That's all right. Think about colors. 2 parents that are
that are the same or different.
Same color and the opposite color to the child. So Ed, where do you see that? Two parents of one color, child of the opposite color.
Generation 2 to generation 3.
Very good, right? And which individuals? So Gen 2, which individuals?
1 and 2.
Very good. Nice. So I would straight away look here. And what I do is I don't even worry about the parents. We know the parents are heterozygous. I quickly write little r, and that means little r is disease because this person is shaded. So I can straight away go, this condition is probably autosomal recessive. It is definitely not autosomal dominant. So when we do this, everyone, we have immediately disproved autosomal dominance or the other pattern of autosomal inheritance. Okay, so straight away, within 3 seconds, if I read this question in reading time, I would have probably gone, it's probably autosomal recessive, which means the answer would be individual 1 is probably A, capital A, little a, and then I'd find what individual 2 is. I think just out of all the options, it straight away leads you to A, right? And then when you actually do the question, you'll be very fast. Good. But anyway, coming back to this, what is the final step? And this is the most cumbersome step. We have to assume and disprove. So let me ask Sarah, what pattern of inheritance are you going to assume and try to disprove?
Could you please repeat it again?
Yeah, so what pattern of inheritance are you going to assume for this pedigree and see if it works?
That it's dominant in.
Think about this. So for the first question, we said, okay, male to female is 3-2, right? There's no tendency for males to be affected, which would be in a sex-linked recessive condition. There's no tendency for more females to be affected, right? Which is sex-linked dominant. So I'm not thinking sex-linked right now. Second question, as Ed mentioned, two parents of one color, child of the opposite color. We just said the child always has to be homozygous recessive. And since they're shaded, they're diseased. And so what pattern of inheritance is this, Sarah, where little r equals disease and it's autosomal?
It's recessive.
Good, autosomal recessive. So our hypothesis or our educated guess is this pedigree is autosomal recessive. The final step is always assuming our hypothesis and seeing if it really works. Does that make sense, Sarah? So you'd be assuming and trying to disprove autosomal recessive. So who's done that? Who's done that? And does it work? Let's go to Kriti. Kriti, since we're assuming autosomal recessive, so little r equals disease, what would every single shaded person's genotype be, Kriti?
Little r, little r.
Good, so you can just go little r, little r, little r, little r. I'll write it at the top. Little r, everywhere, right? And Alyssa, what would every single person who's unshaded, what would their genotype be?
Capital R and then anything.
Good, right? Capital R dash, 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 right? And we're not trying to answer every single person's pedigree. Like I'm quite sure this pedigree works. You can test it out. But just looking here, we know that these two people are heterozygous. So we know this person's genotype. And in the purpose of answering this question, we need to figure out this person's genotype. What must this letter be? Matthew?
Smaller, or could be bigger. Either way.
Could be smaller, could be bigger. Think about this child. This child has two little r's.
Oh, okay, little r, sorry.
Good. Always look at the offspring. Very, very important. Usually the offspring with two little r's tell you so much. This person must be a little r. So much. This person must be a little r. This person must be a little r. Okay. Sorry guys, I don't know what happened, but the second iPad, its audio turned on and so the echo began. So I just turned that all off and reshared. Thank you for waiting. Cool. So yeah, as I mentioned, the answer is individual 2 and 1 are both capital A. So the answer is A. But if you go through and fill this pedigree, it makes complete sense. I'll quickly fill it out for you, right? You can see 2 little r's here from this child, which means this other parent must have had a little r. Looking here, since this parent only has little r's, this individual must have little r's too, right? This one could be anything because this big R could have come from this parent, which means either of these 2 letters can come to this individual, right? And these 2 individuals must have little r's because this parent only has little r's, and that's the pedigree done. So that's how fast you ideally want to do these questions once you get exam ready. Good. Any questions about pedigrees? I think we have quite exhaustively. There's literally nothing else you need to know about pedigrees, right? How to draw them. What's the one thing you're not going to forget when you draw a pedigree? Let's go to Kriti.
The key.
Very good, right? And when you're answering pedigree questions, Sarah, what is the first question you always ask yourself?
Which gender is the most affected?
Very good. Matthew, what's the second question?
The pattern of color shaded.
Good, right? And finally, Rithanya, what's the only way to confirm your educated guess that you make from questions 1 and 2?
Assume the condition and then fill out the pedigree.
Easy, right? Pedigrees are not hard. When you've got these steps, you know what most students would forget. That's what you need to always be thinking. When you're doing biology, you need to ask yourself, what would a band 5 student, or what part of this question makes it hard that I should never ever forget? And then write that down in red, right? A lot of HSC is literally being meticulous, especially for science. Okay, think about the pitfalls that are commonly made. Don't make them. Improve that way. Okay, good. I'm very happy. I don't think we need to go through any more pedigrees, but please do them in your spare time. I think the only other one would be this question, because it teaches you a bit of lateral thinking. I want you guys to quickly do this question for me. Actually, please take your break. I've not given you guys a 5-minute break. If we hit the hour mark and I haven't given you a 5-minute break, feel free to hit the raise hand icon and ask if it's okay as soon as I finish a question. Okay, I think this is more important than actually doing the questions because you come back refreshed rather than, tired for 2 hours because you won't learn as much. So take your break. We'll recap at 3:19. Okay. Make sure you move around, go get some sunlight, okay, get some food in you, and we'll then do this question, and then I'll take you through genetic markers. So we pretty much finished, or get towards finishing Mod 5 by next lesson. Okay, good. All right, see you guys at 3:19. Okay, when we're all back, let's hit the raise hand icon and we'll jump back into it. Cool. All right, when did you all start term 2 of school? What date did you all jump back into it? Britannia, when did school start for you?
School's starting next week on Wednesday for me.
Okay, so you haven't started. Okay, so Feb. Has anyone already started? Okay, right. Just a small word. Maybe this has already happened to you, or maybe it definitely will. But Year 12 setbacks are inevitable, right? So there'll always be some assessment task or exam where you do worse. And I hope this doesn't happen to you, but I'm pretty sure it happened I remember it happened to me, definitely. You do much worse than expected. I think the most important thing is taking time to, grieve over it or run through the emotions. But more importantly, thinking about it very analytically, what went wrong? What mistakes will you not make for next time and learning from it? Right? If you don't have that approach of always optimizing and learning from your mistakes, the setbacks will happen much later or possibly even during the final HC exam. And just remember, the whole year you spend is only 50% of that HSC mark. So the other 3 hours in the exam hall is the other 50%. Okay, so it's kind of like a marathon, but the last 100 meters are weighted like 10 times. Okay, so just keep perspective and make sure you've got your motivation or your vision board or reason for why you're doing this. And hopefully for all of you, you just have the ATAR goal for your course and maybe add 1 or 2 points so you can comfortably get into it. Now, another thing, a lot of people might seem like they definitely know what they want to do, but I want you to know that, even adults, people my age, switch degrees, switch courses, and that definitely might be you as well. So if you're hesitant, you're unsure about what you really want to do, feel free to message me or speak to me after class. We can definitely think about what you like, what you're good at, what the options are. Because I think for a lot of you, it's about HSC study and exams, which is definitely the case. But teachers don't emphasize the importance of kind of planning for your future more broadly. And I think it's because a lot of teachers didn't do that themselves. Cool. Anyway, jumping back to this question. Question 17, give it a go. I will give you about a minute because this isn't too tough of a question. It's more testing how you approach new question types. This is different to the questions that I've shown you, which is either draw a pedigree or what the inheritance is. When you get an answer, hit the raise hand icon. Good. Give everyone about 20 more seconds then. All right, Matthew, what have you cancelled out so far? Any options here that don't look right to you?
I feel like B doesn't look right, but 100%.
Okay, B doesn't look right. Why doesn't B look right?
I just don't know. Just the phenotype. It's not based on the Punnett square. It's just on the phenotype. I don't think so. I don't know.
Okay. Let's go to Sarah. Good. It's good that you're all able to intuitively kind of pick up something's not right about this pedigree. Can anyone tangibly point out any of the pedigrees what's not right? I guess the question you should really be asking yourself is, why are there 3 phenotypes? Because in all other questions, it's you're either affected or you're unaffected. So in what cases would you expect to see 3 different phenotypes? Alyssa? What kind of inheritance would give you 3 different phenotypes, Alyssa?
If it was dominant.
So autosomal dominant? Not quite, because then it'd just be affected, unaffected, right?
Yeah.
Can anyone think about when would you get 3 different phenotypes? This is where you should literally list out every single pattern of inheritance you know, and then cross out the ones that don't have 3 phenotypes. And then when you answer that question, the answer to this question is much easier. Atul, you put your hand up. So, Atul, what was your answer?
I thought it was D.
Good, you'd be right. And why did you pick D? Can you explain it to the rest of the class?
I don't know. It kind of just made sense. I don't really have a reason.
Okay. Very good, but also very dangerous, because you could either be very right or you could be completely wrong, right? And that's what happened in my 2016 Bio HC exam. I came out of the exam and Matrix and all those tutoring centers, I confidently put out the solutions to that paper. And all of them were wrong for, I think, the last 2 questions. And I felt really bad. I was like, oh my God, I butchered the exam. I thought I did okay. But their reasoning didn't make sense. So I want you to remember, especially when you're studying, your reasoning is way more important than your answer. And that's what I want you all to flesh out, right? So when I see 3 phenotypes, I think about the rowan cow, and I think about the snapdragon flower. The rowan cow is splotches of red and white. And then there's a white and there's a red cow, 3 phenotypes, codominance. The other example I think of is incomplete dominance with the snapdragon flower. The flower can be pink, white, or red. And so the only time you will see 3 phenotypes with the inheritance patterns you've studied is codominant or incomplete. So quite literally, you look for the Punnett square, which represents codominance. C is wrong because C is representing a normal dominant recessive trait, right? B is a dominant allele, little b is a recessive allele, right? Another thing you want to check is, does it match the pedigree? Both parents are the exact same phenotype, right? They're crossed. So we've cancelled out C because it's just simple dominance and recessive. When you look at the offspring, this is one phenotype, the recessive phenotype, and these 3 will all represent the dominant trait, right? So C is wrong. When I look at A, I see both parents have completely different genotypes. They'll have completely different phenotypes, and it doesn't make sense. Why are there 2 different genes and 2 different capital and little letters? You don't cross 2 different genes together. You would never cross a B gene with an A gene. That doesn't make sense. A is wrong. And when I look at C, again, the parents have 2 completely different genotypes and phenotypes. And in this case, all offspring should have the exact same genotype and the exact same phenotype. We do not see that. We see all offspring have 3 completely different phenotypes. So what I'm looking for is a Punnett square where both parents have the exact same phenotype. So I look at D, they have the same genotypes, they must have the same phenotype. Tick. And I'm looking for offspring where there are 3 different phenotype combinations. Phenotype 1, phenotype 2, phenotype 3. Phenotype 1, phenotype 2, and phenotype 3. Okay, and AB in our case would be the rowan cow. Good. So that was just one of the more lateral types of questions you'll get. Remember, however hard this question was for your exam, you'll definitely get a question of equal caliber that's lateral thinking in your final HSC. So these questions are so precious for you to kind of think and logically deduce it yourself. Any questions so far? Good. All right, I think we're all sick of Punnett squares by now, so let's move on. Okay, very quick point. I'm just going to run through the rest of the notes, but most importantly, genetic markers. The next half an hour will be dedicated to that, and specifically, I'll run through SNPs. Okay, and we'll talk about what that word means. Polygenic. Sarah, what does the word polygenic mean to you? Just break the word down.
So poly means the polypeptide chain.
Close. Polypeptide. Poly means many. Peptide means the bond between amino acids. So it's telling you many amino acids, right? Poly just means many. It's like polytheistic religion. It's a religion with many deities, etc. Right? So polygenic just means many genes, right? And just to show you, in real life, traits like height, traits like intelligence aren't coded by one gene. Otherwise, scientists by now would have easily been able to tweak that one gene. Heart disease, your genetics play a role in causing heart disease, which is the #1 cause of death. And everyone who's of Asian descent, right, has a higher risk. Now, we found about 60 different genes that increase and modulate your risk of heart disease. That's why it's so hard to just go in there, change genes, and reduce someone's genetic risk, right? So most traits in the real world are polygenic. And what you will notice is when a trait is polygenic, you will see this graph here rather than, based off your year 12 HSC Biology knowledge, if a condition was just coded for by one gene, you can either be affected or you could be unaffected. So it looks like a bar graph, right? There are just two different types of inheritance you can get, affected or unaffected. So if you were to do a line graph, it'd look kind of like this, right? Where no one has an in-between. People either are tall or people are short, right? Whereas in the real world, as you know, height, intelligence, IQ score, everything is on a bell curve, right? Where most people are sitting in the middle, some are sitting lower, some are sitting higher, okay? So if you ever see a graph like this with a trait, I want you to remember, it means that trait is polygenic. There are many genes coding for it. Okay, and that's what allows variations, subtle variations in height, subtle variations in intellect, hair color, etc. Any questions so far? Good. All right, have a read of this dot point, because I'm going to ask one of you, what does it even mean? I don't like the way these dot points are written for HSC Biology. Some of them are just whole sentences. Okay, so what does dot point 3.3 want you to do? If you were to explain this to your friend who's asking you, what do I need to know? Bethany, what is dot point 3.3 about?
Just the relationships, like graphs, to determine characteristics.
Pretty much the conclusion of this dot point, which I want you all to remember, is you are going to be given genetic data. You will have to analyze it, full stop, right? I wish they could just keep it very simple. And the for example is telling you what's high yield. So pretty much just saying, we're going to give you genetic data in the form of tables and graphs. You will need to analyze it. And most commonly, we are going to give you data to calculate allele frequencies. Okay, so in your books, if you're writing this in your notes, the summary of this is calculating allele frequencies. Okay, you can be given some other information, some other data, but it'll all be information you know. Okay, so calculating allele frequencies. Now, to understand how to calculate allele frequency, you'll need to understand why we call it the gene pool. Why do we call the genetic traits of a population a gene pool? Why not, you know, gene home or gene city? Why a gene pool? Let's go to Edward. Why is it called the gene pool, Ed?
Because it's just all the possible combinations of different genes, the whole population.
Yeah, close. So imagine we're looking at one trait or one gene. This is a population, right? Now, every single individual has letters, right? 2 letters specifically for a gene. They can be a capital T, a lowercase t, lowercase t, lowercase t. Now, the beauty of a population is when they breed and have offspring, right? There are usually no letters that are newly made. What really happens is letters flow on from parent to offspring, and then you get an offspring, right? Those offspring carry 2 letters, but those letters will separate in meiosis and randomly be inherited into another offspring. And what you can start to see is this flow on of letters. They kind of fluid and separate here and there like a pool. So the word gene pool is kind of like an analogy to help you understand that a population is just an alphabet soup, and each letter is an allele, right? And the letters will split in meiosis into gametes, and those letters will be randomly inherited by a zygote, which will then do the same to the next generation, right? So this flow-on effect of letters being reassembled, combined, separated is what the gene pool is. Now, the gene pool is kind of like a misnomer. So there's also other genes, right? There'll be a capital R, little r, capital little. There'll be multiple different genes in this gene pool. But a gene pool is referring to all of the genes in a population and all of the alleles of that gene in the population too. So we're not just talking about the T and the R gene. When I mention the gene pool, we're talking about the big T, the little t, the big R, the little r, the relative percentage of big T, the relative percentage of little t. And when you're asked to calculate allele frequency, you're asked to calculate the percentage frequency of either little t or big T in this big gene pool. Does that make sense to everyone so far? Good. Now, to calculate allele frequency, can you hit the raise hand icon? Who has calculated allele frequency before? Or done a question on allele frequency? Good. Good job. All right. So for the rest of us, let me take us through an exam question. Okay. Question 1. I'm going to throw us kind of in the deep end. Okay. Have a read of this question first. Okay, so the question is quite literally just mentioning cystic fibrosis is an autosomal recessive disease. So straight away, if I was reading this question, I would have written little r equals disease, right? So it's this little r allele that causes cystic fibrosis. You're going to come across this condition so many times in your exams, okay, and in your assessment. It is one of the most common genetic conditions. Very common in Caucasian individuals, right? So they get lung infections. They often die by 36. They don't even live half the life expectancy of a Down syndrome patient. It's telling you how nasty this condition is. They go into complete lung failure. They need a transplant. Without a transplant, they die. So it's very, very sad to see people born with this condition. Okay. So we've been told it follows an autosomal recessive pattern of inheritance, and you've been asked to find the allele frequency of the cystic fibrosis allele. So what they're asking in mathematical terms is calculate the frequency F of the little r allele in the population. And when they say calculate the frequency of the non-diseased allele, you're calculating the frequency of the big R allele in the population. Now, let's quickly digress to an example, simpler question before I take you to this question, right? So I want you to imagine if there are 10 people in a population, right? 10 people. Okay, and let's say they all have this heterozygous genotype. Now, if I was asked to calculate the allele frequency of the recessive allele, this is what I would do, right? I would first need to find how many times this little r allele repeats in this population, and then I would divide it by the sample space, which is a total number of letters in this alphabet soup that is the gene pool. So what I mean by that is there's 10 individuals carrying one big R and one little r. Is everyone with me? So the number of times this little r letter appears in this population is exactly 10 times. Everyone agree? What are the total number of letters in this population? There's 10 people carrying 2 letters each. How many letters in total are there? Sarah?
Would it be 20?
Exactly, right? This is why you have to think of the gene pool like an alphabet soup, because that's literally what it is. How many times did this little r appear in the population? 10 times, because each person is carrying one little r letter. But how many total letters are there in this alphabet soup? Well, every person is holding 2 letters, a big R and a little r. So it'd be 10 divided by a sample space of 20. So the allele frequency of little r is a half or 50%. Okay, now we're going to jump to the actual question you see here. Okay, so now it's a little bit more complex. There are multiple different genotypes and there are huge populations, but the same principle applies. Okay, what we need to find out is how many times, what is a number of times that the big T letter appears. Okay, now, let me just change everything to T, right? So instead of R, because I used R for disease, since this question is using T, where little t equals disease, we've been asked to find the frequency of little t and the frequency of big T. Okay, so what we need to find is there are 2 letters, and they're appearing, we don't know how many times, right? So we need to find out the number of times the big T appears, the number of times the little t appears. Now, everyone, there are 634,000 people that are carrying 2 big T's. How many total big T letters are there? How would you calculate that? Let's go to Edward.
Just times by 2.
Exactly, right? Each one of those people are carrying 2 big T's. If there are 2 people with 2 big T's, it'd be 4 big T letters in total. We're finding the number of times it appears. That's it, right? So what we're going to do is we're going to do, well, that's 634,000 times 2. So whatever that is, please get your calculators out, determine what that is. How many times does little t appear? Not even once, because every single person has 2 big T's in that genotype. Same thing, because how many times does a big T appear when there are 96,000 people carrying 1 big T and 1 little t? Alyssa, going to you, how many times does the big T allele appear and how many times does a little t allele appear?
1 each. So 96,000.
Yep. Very good. Good job, right? So 96,000, 96,000. Quite easy. And then again, for the bottom one, right, there are 5,457 people with 2 little t's. Now make sure, even though you're thinking in terms of this alphabet soup analogy, you also take a step back and think, what does this stuff really mean? It's telling you there are 5,000 people with cystic fibrosis. It's an autosomal recessive trait. These people have 2 little t's. These are the unfortunate people who are going to get lung disease, die by 37 because you can't survive without a transplant. Okay, good. All right, but coming back into this alphabet soup analogy, 5,457 people, each carrying 2 little t letters, which means There are 5,457 times 2 little t's. Each person has 2 little t's. Okay, so can someone tell me what is a total sum? And there's 0 big T's. What is a total sum for the number of times a big T appears and a total sum for the number of times a little t appears? Someone quickly determine that.
1,364,000 for big T.
1,364,000 for big T. Good. Thank you. And for little t?
106,914.
106,914. Good job, right? So now it's very easy to answer this question. Well, how many times does big T appear? Well, let's answer the first one. What's the frequency of little t? The frequency of little t is equal to the number of times little t appears over the number of times all letters appear, right? So number of times little t appears is, as Ed mentioned, this many times, 106,914. The total number of letters is equal to 106,914, which is the total number of times little t appeared, plus the total number of times big T appeared, which is going to be plus 1,364,000. Write this a bit neater for us. 364,000. And whatever you get there is your percentage frequency. That's it. So can someone tell me what is the percentage frequency of the little t allele? And someone else do the same for the other. For big T, what is the allele frequency of big T? Anyone got an answer?
7.27% for little t.
Good. 7.27%. I think what that means. It means in the population, 7% of people have some degree of T, the little t allele, right? It exists in 7% of the population. Good. Yep, keep going, Ed. What about big T?
92.73.
92.73%. Yeah. So what this is telling you is in this gene pool, out of all the letters everyone has, there are 92.73% of those letters are big T's and 7.27% of the letters are little t's, right? Very good. That is allele frequencies. That's it. We won't do another question because that's the hardest these questions will get. They're just going to give you bigger numbers and instead of writing genotype like this, they'll say homozygous dominant, heterozygous, homozygous recessive. But you know that's big T, little t, etc. Okay, so key thing is don't forget this way to calculate allele frequency. So many students forget how to do this at the end of the year, and they'll get a question in their trials, and you can't logically work this out unless you remember from this question that you just did. Feel free to do these questions in your own time. Just a little preface, this question is just extension. Doesn't matter if you can't do this question. You will never be asked it to this level in the HSC or trials. I just wanted to really test you out. I Google searched everything about Huntington's disease, put it into a question. Yeah, and the same for question 3. Okay, it's a bit more mathematical, but it's the exact same approach. Good. Okay, I want you to do this question in your own time. So important. So important. This is a very good lateral thinking question. Okay, when you read through the above 2 questions. All right, in the last couple of minutes, we'll talk about SNPs. Can you hit the raise hand icon if you've read about SNPs? Anyone read about SNPs? Good. It's done a little bit of reading. All right, that's okay. Good. Just clarifying, you're starting school on Monday or the week after? When does school start for most of you? Matthew, when does school start for you?
Next week, Tuesday.
Okay, so it's coming Tuesday. Okay. Well, you still have a couple of days, as ideally, by the time school starts, at least have a full read through of Mod 5, right? At least the content. So when school starts, we can kind of go a little bit faster as well. I'm only saying this because this next part of Mod 5, it's not hard in terms of calculation, etc. It's a little bit challenging for students in terms of concepts, right? And you might know whenever it's hard concepts, the longer it's been in your brain, the more you're able to digest it and make sense of it. Okay, and that's the exact case with SNPs and short tenor repeats. The earlier you're exposed to it, the more time you have to think about it, think about what doesn't make sense, work it out in your head. So by exam time, this stuff is very easy, because often every single year I hear for Mod 5, students say this part of Mod 5 is the hardest because it's conceptually hard. Okay, there, we'll make it easy for us. All right, we'll start with the word SNP. Let's first understand what this word means. Single nucleotide polymorphism. Okay, what does the word nucleotide mean to you? Let's go to Sarah. So what does nucleotide mean?
The base pairs in the DNA.
Good. Is it just the base pair? Because remember, the word nucleotide is very specific in its definition. Alyssa, moving on to you. What does the word nucleotide mean? Nucleotide.
Is it like the thing that makes RNA and DNA?
Yes, good. But remember, the word you don't want to use is thing in biology, because everything is technically a thing. It's a base sugar and a phosphate, right? So it's the repeating unit of DNA and RNA. Okay, base sugar phosphate. I want you to remember that. Okay, so the word single nucleotide polymorphism is talking about the nucleotide or the base sugar phosphate. Sorry, I'm just going to. So I think your mic is on. Do you mind just muting? Thank you. Great. All right. So as I was saying, nucleotide is a base sugar and a phosphate. Now, which part of that actually varies? A sugar and a phosphate don't really vary. Forget about RNA and DNA. The only thing that really varies is the base. So even though we're saying the word nucleotide, we're most specifically referring to a base. Okay, so far this word translates loosely to single base. Okay, what does the word polymorph mean? If I morph into something, I'm changing form. What does poly mean? Many. So when you put this together, single nucleotide polymorphism means single base variation. That's it. Single base variation. You might be thinking, well, of course, we have so many variations in our letters, right? The letters that make up your instruction manual are different to my instruction manual. Now, this is an interesting thing. They're actually not that different at all. If you put your instruction manual, so your entire DNA string, next to mine, we would have the exact same set of 300 or so letters. The first 300 letters in your DNA sequence in your chromosome 1 and in my DNA sequence in my chromosome 1 will be the exact same. The A, T, G, C, A, C, C, T, A will be the exact same. What will vary will be around at the 300 to 400th base. There'll be one letter that's different. And interestingly, that exact same spot is different for everyone. It'll be different for you, it'll be different for me, it'll be different for Matthew, Thania, Ed, will all have a different letter at that one spot. Okay, So when scientists saw that, when they actually sequenced all of, you've heard of the Human Genome Project that was done in 2003, where they got hundreds of people and they wrote down every single letter of their DNA. It's the first time that ever happened in history. And they were surprised because every 300 letters, there was one variation in one letter or so. And so scientists looked at this and they called it a single nucleotide polymorphism. They said, when I look at this person's DNA, when I look at this person's DNA, as you can see, they're the exact same here, the exact same here, the exact same here, but after about 300 to 400 bases, most people have a variation. Okay? Now, there are a lot of variations. There are some variations where only 1% of people had a different letter. There are some variations where the majority of people at that exact same spot, like I said, had a different letter. So what scientists did was they set a threshold. They said, when over 5% of people have a variation in their DNA at a particular spot, we call it a SNP. Okay? Sorry, not 5%, 1%. Okay? So when more than 1% of the population have a variation at one particular spot in their DNA, we call that a SNP. So what I mean by that is, let's say that 99.9% of humans in Australia have a C and a G at this spot, and only 0.1% of people have an A at this spot. This would not be called a single nucleotide polymorphism. And it's because this variation is not present in greater than 1% of the population. It's only present in 0.1%, which is too small. We don't care about that. Okay, so this is an arbitrary or random number that scientists ascribe to this definition that you need to know, right? So to summarize, a SNP is a single base variation in DNA that must be present in greater than 1% of the population. I want you all to write the 1%, because if you don't say that in your exam, you will lose your mark for your definition. Any questions so far? Good. All right. I think for now, we're going to leave SNPs at that. But just remember, they're a term that scientists or humans made to describe variations in DNA. That's all it is. Okay, base variation greater than 1%. I want you all to underline, highlight in red this part, because if you do not say it, you will lose marks. Okay, and it's part of the definition. Any questions at all before we finish today's lesson? Okay, so by next week, I expect all of you to have read through SNPs. I want you to have read through profiling, DNA profiling and DNA sequencing. If you can get that done for me, we can probably finish the entire lesson or finish mod 5 by mid to end of next lesson. And we can get started on mod 6. Good. Has anyone already finished mod 5 at school? No one's finished 5. Okay, good. All right, anyone up to this at school? Anyone learnt about SNPs at school? No? All right. Okay, so most schools are going a bit slow. All right, good. Any other questions that we might have for this week?
So
Yeah.
for 6, you know how there's like dot points where you have to give examples? In your notes, you've given like 6 examples.
Yeah,
Do you
don't
need
6.
Or
No.
do you need 2, 3?
Very good question. Literally 1 is fine. 1 is fine, right? I give so many just so you have like a full-on understanding, and if you do come across another example in an exam, you go, look, I've seen it before, right? Remember this, the HSC does not care about how much information you've memorized. You'll do the exam and you'll find, I don't even use any examples, which is most commonly the case. So examples aren't too important. Remember 1 at most, okay? But it's much more about the application. Good. The last thing I want to talk about, guys, is I am starting surgery. I'm starting upper GI gastrointestinal surgery for the next 10 weeks. So it's going to be quite intense. And they've also rostered me a couple of, I think, weekends, because as you might know, hospital's always working. I think it's only one weekend this term, but what that might mean is you may need to reschedule class 1 week of the term. I'll let you guys know the exact date very shortly. But I just wanted to ask, actually, we can figure out the date which we reschedule it later. But what I wanted you to make sure is make sure you're checking Teams. If you ever see a Teams notification on your phone, just make sure you check it as soon as you can about class time changing, etc. But I'll let you know within the next 3 or 4 days what day we won't have class that weekend, and we'll organize and make up for it. Okay, good. Or alternatively, I may be able to get a cover. We'll see. We'll organize, and I'll get back to you on that. But good. All right, it was a great first lesson. I hope you all learnt a lot about SNPs and pedigrees, and I hope you all get back into the swing of things. Okay, see you all next week. Bye, guys.
Thank you.
Bye. Pretty cool. You had a question?
Yeah, you know, for the module 6 folder you sent on the Google Drive.
Yeah, don't worry about that folder, Critty. So I actually resent it as 2 individual accesses. Did you get that? You would have got mod 6 bio notes, mod 6 bio questions separately. That's just what was in the drive.
Oh, I only got the one email with like the link to the Google Drive one, and then it says that I don't have access to it. So.
Okay, well, I'll look into it, but yeah, don't worry about the folder. You'll get individual access to each of the documents. Okay.
I also don't have the module 5 one.
You don't have access to it online, or you don't have the printed copy?
Online.
Okay, log into the edxlearning.online website. When you do that, let me know what email you logged in with, and I'll get you access. Okay, it's in the My Resources section of the edX website.
I went there last time and it didn't work. I don't really. I put in the edX email and then it like says, I don't know.
Try logging by your Gmail and then send me a Gmail. Okay.
Oh, like my normal Gmail.
Yeah, normal
Okay.
Gmail. That works. All right, I'll see you next week.
Thank you.
Bye.
Bye.